INCJN. Okay, this thing. Okay, it's going to be, either determinant of A if I go to J. Obviously, that's the case, right? Because if I go to K, it becomes the definition of determinant of A, right? So this is obviously true. And the zero, otherwise, this is, actually, the proof is more important for the second part. If I and J are different, this thing will end up to be zero. Okay, because of that, so you can write that as a delta ij determinant A. What is delta ij? By the way, the delta ij just means that the delta ij means it's a 1 if I go to J, it's 0 if I does not go to J. Okay, that's a mathematical notation. Okay, so you can see that magically it's like a equation. As I go to J, delta ij becomes 0, right? So the whole thing becomes 0. Okay, delta ij, if I go to J, it becomes 1. So if I go to J, obviously that's the case. And follow like a definition of determinant. But if it's not, if I is not equal to J, okay, it will be interesting. Okay, because you can sort of, represent the left-hand side as the determinant of the right-hand side, this matrix, where, okay, you have two, the I row and the J row are identical. And you are trying to expand through the J's row. Sorry, I's row. So you are trying to expand through I's row. So that's why you get AI1, AI2, AIN here. But because these two rows are identical, so the other part you're getting like CJ1, CJ2, and so on. So if that's the case, think about that. That means you are computing a determinant of a matrix that has two identical rows, right? We have already shown you that if a matrix has two identical rows, its determinant has to be 0, right? Okay, so that's the result of of the previous proof, actually. So here's a very, very important thing. Like we are now trying to connect the determinant with the row operations. Actually, like we are doing like something more, aggressive. Because in chapter 1, we are only discussing elementary row operations, right? But here, okay, not only we can consider row operations, those elementary row operations, we can also consider some we can also consider elementary column operations. Okay, column operations. Although we only discuss discussed elementary row operation in the chapter 1. Okay. But if you have trouble with those column operations, let's forget about those column operations first. Let's focus on row operations. Once you understand row operations, I mean, it will be easy for you to carry over the similar idea to column operation. Okay. The first one, if B is obtained from A by exchanging two rows, then determinant of B equal to negative determinant A. This one, okay, we can prove. Okay, we exchange two rows. Exchanging two rows is one of the elementary row operations, right? We know that. And we can assume we can do this proof by induction. Okay. Again, in order to exchange two rows, you have to have at least two rows. So the base case starts with like the base case n starts from 2. Okay. So let's look at A, B, C, and the result, the exchange, C, A, B, and you can see that this is obviously A, D, this is AD minus BC. So this one becomes like a CD, so BC minus AD, which is like exactly like satisfy what we want. Determinant of B equal to negative negation of determinant of A. Okay, this is the case. For when A is 2. And then when A is more than K, assume this is the case. Okay, and then when A is K, okay, then, okay, we basically like expect to any additional, a different row, So it's let's assume this is AI1, AI2. AK2, sorry, KN2. So it's going to be AI1 and C I1 plus AI2 CI2 plus AIN CIN, right? And then, you get rid of, for example, let's look at CI1. You get rid of all the other remains the same. But if you get rid of this column, this row, this column, this row, you see, if you exchange these two rows, okay, the other one, AI1, okay, the other one is exactly like just the -1. This is -1. I plus 1 times determinant of that AI1, right? So this is like I plus 1. And the determinant of, I don't know how to write it. It's AI1 plus prime. The prime means that we exchange these two rows, right? So we know, according to the induction hypothesis, this one is like, this one, that differ by negation, right? According to induction hypothesis, right? Because these two matrices, the only difference is exchange two rows. Like the induction hypothesis tells us that if you exchange two rows, like when the size is lower than k, if you exchange two rows, the determinant of the original matrix is going to be negation of the determinant of that matrix after you exchange those two rows. Okay, so these two is different by only one negation. So it applies for all the other things. So obviously, we change the row. They are different by one negation, right? Is it okay? 你就看说每个 CI1 就把它打开来，其实就是那样子，它就是中间换那个，按照那个 hypothesis， 它就是差一个符号。每个差一个符号，你把那个符号拿出来，是不是就是整个差一个符号？整个差一个符号，人家讲学的话，不是徐老师啊，反正就 induction hypothesis。Induction step is satisfied, so we have that problem. Okay, so for that row operation, we have that. So if B is obtained from A by multiplying a row by a non-zero constant C, then determinant of B equals C times determinant of A. This is also very easy because this one we don't even need to use reduction. If you multiply a row by C, by constant C, non-zero constant C, then every element will be multiplied by that C, right? Okay, then if this row is AI1, AI2, AIN, then, okay, the result is C times AI1, C times AI2, or C times AIN. The original matrix is determined. If you extend through this row, it's going to be AI1, capital CI1, plus AI2, capital CI2, plus AIN, capital CIN. And the resulting matrix is determined is going to be C times AI1, and this one doesn't change, so it's capital CI1 plus C times AI2, CI2 plus C times AIN, capital CIN. So you can see that every term you have a C there, right? So you just get, just put a C. That's how you get it. You don't even use induction. Okay? The last one. If B is obtained from A by adding a multiple of a row, okay, of A to another row, okay, of A, then determinant of B equal to determinant of A. This one, proved by induction. As I said, most of the proof is done by induction. So, in order to do that, you need at least two rows, right? By the way, all my proof are about rows, but obviously they apply to columns too, right? The idea is similar. So I will skip those. But so the base case will be A, B, C, D. So the determinant of that will be A, B minus B, C. And if you try to multiply, A, B, multiply first row by a constant, add to the second row. So it's going to C plus K times A, and E plus K times B. So the determinant of that is going to be, you can do this one, so it's A, B plus K times A, B. A times B plus K times A minus BC minus K times AB. So these two terms cancel each other, so it's going to be AB minus BC. Right? So for this case, this can be easily verified. Right? Okay. So how about assume that it is true for when the size is lower than K, then when the size is K, so you try to multiply this one with K and add this one. Okay. So let's assume this is the row i's row. This is j's row. Okay? Then, again, you try to expand by another row. Okay, try to keep these two rows intact. So, it's going to be, say that it's A, P1, A, P2, AK. Okay, you try to expand through this piece row. And then it's going to be A, P1, C, P1, plus A, P2, C, P2, plus A, P, K, C, P, K, right? Right? But each of these, you get rid of this, get rid of this. So you can see that these two rows, I mean, the operation is still there, right? And according to our induction hypothesis, this will be exactly the same as we are not doing that, right? It will be the same as if we are not doing that. So this will be the same as if we are not doing that, so this will convert it back to determinant of original shape, right? Right? 就是我们这边不是假设这个是我们已经把这个 I row 乘上 K 倍，然后加到 J row 嘛？那这每一个我刚刚讲过说，我们这每一个，因为我们把这个 column 去掉，这个 row 去掉，这两行还是有这个性质，对不对？这两个 row 还是有这个性质。那这个就跟我们刚刚 induction hypothesis 已经讲过，如果说它的 size 小于 K， 那这个就会跟原来那个没有做的那个是一样，对不对？那个没有做的就是原来那个 AIJ， 对不对？ capital AIJ。 flip，就是flip就是回到那个 determinant page。所以这个东西有做跟没做 ，OK，these two are the same according to reduction。OK。Okay, so I'm sorry I skipped like that group. This group. This group. I will give you the proof by email, okay? And also I will give you like the practice question and hold the second quiz near the end of the next lecture. Okay, any questions? No question, I will see you next week. Okay?